Hi, I'm Athena Hansen Ahern, conference producer for Technology Networks, and I'm here to introduce our final talk of this year's Laboratory of the Future online symposium, Advanced and Continuous Flow Reactions in Chemistry and Polymerizations. I'm pleased to welcome our speaker, Rigoberto Advincula. The first half of Rigoberto's session will focus on his team's research in the field of flow chemistry and provide some context before he moves on to the second of his session, which will describe how his group are utilizing artificial intelligence and machine learning to advance their research. Rigoberto is a governance chair professor at the Department of Chemical and Biomolecular Engineering, University of Tennessee. He received the Distinguished Herman Mark Scholar Award in 2013. In 2018, he was elected National Academy of Science Technology, Philippines, and has been recently appointed to the World Economic Forum Advanced Materials Council. His group does research in polymer materials, nanocomposites, colloidal science, 3D printing, hybrid materials, and ultra-thin films for applications from smart coatings to biomedical devices. He is passionate about mentoring students and helping other countries in their STEM programs. A warm welcome to you, Rigoberto. Following the presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. You can also use this feature to connect with attendees and discuss the talk. So feel free to take advantage of the chat system by introducing yourself and sharing your thoughts during this presentation. And if you experience any technical difficulties during the presentation, please request help using the technical help icon in the menu on the left-hand side of the player. Without further ado, I will hand over to Rigoberto to begin his presentation.
Okay, well, thank you, Athena, for that generous introduction. First of all, I'd like to thank also Technology Networks for this opportunity to give a talk on advanced and continuous flow reactions in chemistry and polymerization. As you see in my slide, I have an email, and you can contact me with regards to this talk and other future research interests. And although I'm with the University of Tennessee, I'm a group leader at the Oak Ridge National Laboratory Center for Nanophase Material Sciences. Now, a number of this work is also represented by my group at Case Western Reserve University, which was my former institution before moving to Oak Ridge and University of Tennessee. And as you can see on the next slide, Oak Ridge National Lab is a national facility with the Department of Energy, and I'm part of the Center for Nanophase Material Sciences. I'm also part of the Institute for Advanced Materials Manufacturing at the University of Tennessee. And you can see a nice clear day on an orange and white football stadium at the University of Tennessee. Now, most of our work deals with nanostructuring of materials, surfaces, characterization involving surface analytical techniques. And this is a picture of my group from last year. I do have still some PhD students at the university at Case Western Reserve, and they are also represented with our work. Now, when we deal with polymers at interfaces and colloidal phenomena, we are looking at the kinetic and thermodynamic behavior associated molecule. They can be associated with films or gels or micelles, different types of membranes where the physical chemical properties, the structure chemical property relationship is very important. But as you can see in this representation, polymers can be represented as nanomaterials as well because they have that dimensionality and also unique reactivity at the 100 nanometer scale and below. On the other hand, as molecules, macromolecular architectures and microstructure are represented by their connectivity, their branching, their shape, topology, and their ability to form mesophases or different types of phase-separated domains that can be observed by microscopy. And a lot of these structure composition property relationship studies, when mastered, allows us to produce products like plastics, very relevant to the way a modern society works. Now, our group in particular, we have been very interested with the synthesis of organic and polymer materials, including light-emitting materials, conjugated polymers, conducting polymers, as represented by these polythiophene, ladder polymers, and polycarbazole fluorine copolymers. On the other hand, we've done a lot of work on dendrimers and hybrid nanomaterials that are represented here, where energy transfer and charge transfer properties are associated with their architecture or size. We have also worked on what we call supramolecularly knotted and templated polymers, where we can order them based on their topology, mimicking that of similar to supramolecular chemistry, but in a larger ring or polymer size. On the other hand, we've also worked on grafting of polymers on surfaces, which involves control of charge and surface density, as well as surface-initiated polymerization. So you can see that our group is very rich in experience and focus on materials, polymers, surfaces, and the characterization thereof. But today, I would like to emphasize that a lot of the advancement that can be done in the future will rely on automated labs, autonomous labs, or even the application of artificial intelligence and machine learning. And so today, I'm going to focus on how we have been synthesizing of late polymers based on continuous flow chemistry and reactions. You see, a lot of the polymers today, when produced in scale, requires a pilot reactor. And these reactors are quite expensive, and they produce kilograms to even hundreds of kilograms scale. Although done in a continuous flow or pressurized environment and production purposes, they are not as versatile as smaller bench scale or even microreactors or microfluidics for the study of kinetics and thermodynamics of reaction mechanisms. Thus, a field that has grown in the last 20 years is the use of microfluidics and microreactors in the study of organic chemical reactions or limited production in the bench scale. And a lot of this development, as you will see, has advantages and supplants what is traditional a laboratory procedure that is based on using flasks or reactors based on glassware, not pressurized and not part of a unit. Here, when we take a look at the mixing environment, although dominated by an impeller in a flask, takes a very different environment when confined in microreactors or microfluidics. So for example, the design of that mixing environment, whether it's T or Y-shaped micromixers or focused enhanced mixers, droplet mix micromixers, take advantage of the confined pressure and temperature system that can be found in a smaller footprint. And therefore, the Peckley number or the turbulence experience in small micromixers or mixing systems is very important in order to achieve pressure, temperature, electrokinetic, dielectric-phoretic control, and so on. Now, differentiating this from a traditional reaction. So when you think of chemistry, we think about flask, reflux, condensers, things that are done with a magnetic stirrer and so on. And I would say that is your traditional laboratory. And in fact, this is still very much taught when you take organic chemistry as an undergraduate or a chemistry major, simply because the realm of flow reaction synthesis has not gone into the undergraduate level or even high school level to a significant degree. But as you can see in this first part of the talk, there are inherent advantages of switching to a fluid flow or continuous flow direction, whether it be control of the residence time, control of the reaction temperature, pressure, and especially in the study of catalysts. So further differentiating a batch reactor from a flow reactor, you see one of the biggest problems of a traditional batch reactor is the distribution of heat. It is very inefficient in that most of the heating occurs only in the sides of the flask, and you need to have a good steering mechanism to distribute that heat. Furthermore, since it's an open system, it takes hours or even days to complete a reaction. On the other hand, a flow reactor allows you to control the specific surface area or the entropic um, confinement of that environment for mixing. A high specific surface area has advantages in terms of thermal transfer. A flow or controlled flow nature eventually leads to easier separation and the use of heterogeneous reaction or packed bed systems or catalysts. And it is also possible to control the sequence of the reaction. So what I'm going to show to you are some examples that are found in organic synthesis, material synthesis, and polymer synthesis using flow chemistry. You see, the field of pharmaceutical chemistry, medicinal chemistry are shifting towards the use of flow reactors. And as you'll see here, the inherent advantages comes out in terms of yield, control of the enantiomeric excess or reactions under asymmetric conditions, and the use of different types of initiation or reaching that activation energy of the reaction, whether it's thermal, UV irradiation, or use of microwave. And in this first example, you can see here a simple carried out to very high conversion as well as EE. And then the bottom example shows a reaction that involves the amidation or very efficient amidation rather of a drug precursor. Another exhibition of this advantage is in the form of pericyclic reactions, as shown here. The control of this light-driven or temperature-driven reaction can be done both in homogeneous and heterogeneous conditions. And as you can see here, high reaction yields and selectivity is achieved. On the other hand, we have seen advantages of using a microfluidic system in the synthesis of particles. So in an oil and water environment where the reaction, for example, allows one to isolate these perfect spheres for forming hexagonally packed structures, or the cylindrical particles can be done under flow. One can also use micellar nanoparticles in microfluidic systems. That means a polymer like this PLGA PEG black copolymer enables the surfactant to form distributed micelle sizes. And by controlling the flow ratio, one can control the size of the particle. In the area of gas phase reactions in a flow systems, if you are a chemist, you know that gases and liquids do not necessarily like each other. But in a continuous flow reactor system, it is possible to control the diffusion of gases in and out by controlling a two-phase tube where you can have a liquid and a gas flowing at the same rate. A controlled reaction. And this is, for example, done using, let's say, a Teflon tube or other types of Tygon or specific diffusion controlled systems. Several examples here shows that gas phase reaction in a flow synthesis system is achieved easily, whether introducing oxygen, carbon dioxide, ammonia, ethylene, or other reactive reagents based on gases or vapor phase control. And several of these syntheses are again relevant to the drug industry. Now let's turn more towards the polymerization in a conventional reaction platform. Again, most of the examples I've shown you even on our work was done under batch reactions. So the figure in the left is relevant and is a very common implement in our lab and in many labs or all over. Now, the confinement of a reaction in a very small volume may involve micromixing, but what one wants to achieve is where the initiator and the monomer ratio is controlled in a very small space. In doing so, you have a very efficient distribution of heat or catalysis. And in other words, the collision theory is pretty much controlled in an environment like a micromixing or even a confined continuous flow environment, resulting in a well-defined polymer. So a number of polymers that we make in our lab involves controlled radical polymerizations like ATRP or RAP, or even anionic ationic polymerization. Polyolefins is very much all polyolefins constitutes, of course, your polyethylene, polypropylene, polystyrene, and other vinyl polymers. And this has been shown to have unique advantages, of course, with flow chemistry. So several examples are shown here. Here's one where using a free radical initiator like AIBN allows one to achieve controlled molecular weights of methyl methacrylate, butyl acrylate, with even lower polydispersity than when done in a batch reactor. And by controlling the residence time or uh, reaction or flow rate, one can control the molecular weight. So in principle, the higher the residence time or the slower the flow rate, the higher the molecular weight. And this is observed in many, many cases. Here is a example of an ATRP done using a microfluidic system. Again, by controlling the flow rate, one can achieve a higher molecular weight with a slower flow rate, as observed in this GPC trace. Here is an example of a RAP polymerization producing a black copolymer, again, based on continuous flow chemistry with either segmented or continuous flow conditions. And this has been, of course, reported way back. So the introduction of the monomer is in sequence. First, introducing monomer A, followed by monomer B, and you can even alternate or introduce monomer C. And that is the advantage of a microfluidic or continuous flow reaction in that you can have sequence control. On the other hand, here we have an example of a cationic leaving polymerization showing the control of the use blocks and diblocks of materials. And lastly, this is a ring opening polymerization to produce poly um, peptides based on the NCA monomer, where the flow rate, again, shows a control in molecular weight based on high to low flow rate. And high to low flow rate translates to low molecular weight to high molecular weight. So hopefully I've convinced you of the advantages of flow chemistry at this point in these examples. And what I'm going to show you now are some of our work, and then we will go into why this is important for the future of manufacturing as well as design of the laboratory employing AI and machine learning. But first, this system that we have used is based on a Thales nanoreactor, which we can control the temperature and pressure, as I've shown you in previous slides. This basically is based on confinement of the reaction volume, a very, very small footprint, and then a sequence control allowing the introduction of the monomer initiator or a sequence of monomers under flow where we can control the pressure, temperature conditions. In fact, Thales Nano has several reactors that have been used heavily for production of hydrogen, even for deuteration, or other types of organic synthesis modes under controlled pressure and temperature. So in this paper that we published back in 2017, it is actually very important to emphasize here that this polymerization was done in water. Why was that important? Well, in the regime that we want to save the environment by not. And this is only possible by doing it under flow. So in this RAP polymerization using ethanol water, again, the assumptions we made are the possible advantages and efficiencies. But in particular, we are interested in controlling the molecular weight and polydispersity of the material. So first we synthesize here, shown by NMR, the chain transfer agent based on this thioester, and then we loaded this on the column together with the monomer, PEG methacrylate, and the ACVA or AIBN analog, which again is an initiator for free radical polymerization. But in this case, since we are using a controlled pressure, we can increase the temperature and therefore achieve a shorter uh, shorter half lifetime for the initiator, and therefore the reaction can be carried out in minutes rather than hours. Again, another savings for uh, doing things in the laboratory under flow. So in this schematic diagram, we introduce the monomer, the initiator under various ratios together with the chain transfer agent, and then we achieve the corresponding polymer. And as you can see here, the advantage of doing things under flow is we're able to heat the system up to 100 degrees C, resulting in a half-life to about 7 minutes, whereas most AIBN type of reactions are done in hours. We can do our reaction in minutes. Furthermore, as we produce the polymers, we can characterize them using infrared spectroscopy and NMR. Indeed, we get polymers, but more importantly, we can measure the molecular weight. This first system with the corresponding absolute molecular weight using light scattering GPC. But here in this table, it shows how we can control the reaction. So for example, if we have certain conditions where we control the flow rate. So by using a flow rate, we can get a higher molecular weight. Conversion is more or less anywhere between 18 to 60%. Also, on the other hand, by controlling the ratio, we can get different types of molecular weight. And then finally, by controlling both the temperature and pressure, we can use the conversion for reaction time as well. And this was published back in 2017. In another paper that we published back in 2019, this involved the grafting of polymers on silica microparticles and the demonstration that we can make black copolymers. This involves modifying the particle surface, attaching them the chain transfer agent on the surface, washing the particles with a solvent, adding the monomer, taking the particles out. Well, now, what I'm referring to is a traditional method of reacting or producing these core shell particles in a flask. However, we can simplify things in a continuous flow reaction by first modifying the particles on the surface, washing the particles, introducing the monomer, changing the monomer back and forth if we want to, but then there's no more taking the particles out of the reactor. In other words, the whole reaction can be done under flow. So taking this cue, we synthesize a chain transfer agent that can be attached on the surface with silane chemistry, as shown here. And then we introduce this on a particle. This case was the form of a silica gel and some metal oxide particles or metal oxide particles. Here, you can see the attachment on a surface, followed by reaction based on the chain transfer agent, and then catching the product. So the whole setup was done in a column where the particles are packed in a column. And I'll show you later how those particles look like. On the other hand, as I demonstrated, as I've shown earlier in the schematic diagram, we can then switch from one monomer to the next. So the first monomer that was introduced was based on the PEG methacrylate monomer. After washing any excess, we then introduced the N-isopropyl acrylamide monomer, so that the end result, as shown here, is a black copolymer or a dye block that is attached to the surface. And we prove this by looking at the thermogravimetric analysis, which shows the grafting of the monomer initiator followed by polymerization. And in looking at the reaction rate or flow time, and also the ratio between the initiator and the monomer, clearly we can see that the slower or longer flow rate time or residence time produce higher molecular weights or more grafted polymers, as well as the introduction of a higher concentration of monomer. And then finally, by controlling the chain length, we can observe this also by GPC. So the traces here actually give us the corresponding molecular weight. The polydispersity is around 1.2, increasing concentration or residence time or flow rate. And then we characterize this black-copolymer based on IR as well as TGA. Okay. And then here you can see the corresponding molecular weight after degrafting from the surface, showing the difference between a homopolymer and a black copolymer. Okay. And the surface has been modified, as shown by the change in the wetting behavior. The polynipam is the last monomer, which is temperature sensitive. So using the critical solution temperature, or LCST, when we heat up the sample becomes more hydrophobic. In this last example, we then utilize this system to graft hyperbranch polymers. In this case, an enimer was used, where the enimer or initiator monomer facilitated the reaction of this DMA-EMA monomer, resulting in a amine group, a saturated amine group present on the surface in a hyperbranch form, as shown schematically here. And the same sequence was done by packing the particle with an 80 RP initiator this time, and then controlling the ratio between the monomer and the enimer, and also the residence time. And as you can see here, by increasing the amount of the enimer, we essentially control the branching. The higher the enimer, the higher the branching. But we can also control the molecular weight based on that ratio. And both TGA, NMR, and IR prove this work. But probably it's more identifiable if we look at the modification of the particle. Spheres of silica or glass. We then pack them in a column and then introduce the hyperbranch, resulting in a core shell modified particle. Using XPS, we prove the composition, but also because of the LCST behavior as well as the pH condition. When we change the pH, we change the wetting behavior, or when we change the temperature of the surface, we change the contact angle or wetting behavior. And we demonstrated utility of these particle systems, let's say, for drug capture. So in summary, what I've shown you are actual experiments and reaction cases that we've done in a flow chemistry lab. And you can see here a unit operation, which essentially can be optimized either by controlling the reaction conditions and using parameters like temperature, pressure, monomer, initiator feed ratio, and so on. Now, why does that matter? Well, let me talk to you about artificial intelligence. So I have to tell you that a number of these images are part of the Creative Commons licensing, and I also attributed the websites where I derived them. So artificial intelligence basically relates to the use of algorithm, neural networks, or even deep learning to optimize systems or to bias a particular application or a process condition to the outcome you want. Or it can help you in decision making. And so artificial intelligence has been applied widely in many systems or applications. And a typical synthesis laboratory is not an exception. In fact, whether AI is applied for decision making, optimization, or study of social condition, or as predictive models. Perhaps these three terms, material synthesis, characterization, scale-up production, are one of the salient advantages you will see as more and more operations, studies, scientific investigations gravitate towards using AI, ML, or DL. So artificial intelligence is the big catch-all within a subset of artificial intelligence. You have machine learning, and whether you're dealing with 100 samples or less, you can use simple linear regression, other types of statistical methods, and so on. On the other hand, deep learning becomes very important when you have a very large number of samples where you want to simplify that relationship, and therefore things like neural networks or different types of encoder or other network mechanisms as shown here becomes very important. Now I'm showing you actual schematic diagrams that was borrowed from a literature recently highlighting work at Oak Ridge National Lab. And as you can see here, a lot of the AI applications are gravitating towards characterization. So characterization means we employ X-ray, Raman, NMR, imaging methods, UVVs, or perhaps in the future, neutrons using AI. We can use imaging based on SEM, STM, STEM, and AFM, which stands for scanning electron microscopy, scanning microscopy. And you see a number of literature that is already pointing towards the advantages of using AI ML towards characterization. However, I want to point that AI ML can have very important advantages in terms of production, manufacturing, or even high throughput synthesis in a bench scale, just like what I've shown you. So for example, in additive manufacturing, it's being used to optimize layering and properties using, let's say, 3D printing. On the other hand, other types of process conditions, whether it's fabrication, machining, they will take advantage of AI ML for simplifying tasks or optimizing design. On the other hand, engineering unit operations that are based on flow, thermal distribution, kinetic control is ripe for AI ML. And in several examples here, as I'll show you later, what we're trying to do at Oak Ridge, you will find that this is the way to go. So as I emphasized earlier, artificial intelligence is the big canopy. Within this, you have machine learning and deep learning. Again, this is divided by the number of samples or the number, or rather the target by which you want to mine data, as well as to get an outcome for a very important task that is sequential. In many ways, this is a exercise on risk-based risk-reward analysis, but also it's an example for convergence. So you want to have factors that converge to a point advantage of reiteration or optimization for the next batch. Or if you have an autonomous condition where you let the algorithm work, it will come to a decision minima where you have all things work. Or if you look at entropy, you minimize entropy. Or if you want to look at kinetics, you bias it on one type of kinetics direction. So this involves workflows. That means you need to collect data. You need to have sensors. Sensors that are embedded, sensors that are part of an online reaction, sensors that are based on spectroscopic, microscopic, electrochemical signals. You then take that data, you then train that data, and develop an initial algorithm. The algorithm can then be used to provide a feedback loop to test that initial set of conditions, and then you repeat the process. Now, again, monitoring the sensors in an online experiment is very important, and the development of that hardware is a hard task, literally, because of the API and the interfacing that is involved between the computer and the sensor, and let's say the flow condition. On the other hand, once you optimize this type of exercise, you can arrive at models. Rather, you can arrive at algorithms, which can be satisfied both by the initial model or the optimized model that can be applied for that particular process condition or flow reaction. So automating this whole process in a science domain experiment or a process condition is what we're talking here. We're talking about optimizing laboratory procedures, post-dose reaction conditions, so that not to take the human element out of it, but to shorten the process or to improve the production yield. So this, again, is an example coming from work at Oak Ridge National Lab, where a materials design based on, let's say, looking at the change in the band gap between different oxides or different organic materials or organic electronic materials, means that we can use an initial DFT simulation or calculation to train a neural network system that allows us to simulate the best optimized design or set of conditions or process conditions. We then test the sample, and then we can, in fact, create a library of these different materials, and then finally down select samples based on that fitness criteria. And upon optimizing this using an algorithm and, let's say, correlating it with DFT calculations or other semi-empirical methods, one can arrive at the ideal structure. Now, here we're not even talking about the reaction itself, but just designing the materials before you do the reaction. And here you can see AI already plays a big role in the design of reaction before you even make it. So here I described to you an initiative that we started at Oak Ridge National Lab last year. It's called the AutoFlow system. It is now part of the Intersect initiative. It has been led by me of late, but it was work done Brahma and Ilya, and we have been employing this mechanism to optimize reactions in our lab. So as you can see here, the project flow, or literally the flow of a continuous flow reactor, involves a process where we have an initial design of the synthesis or the target material. We then start generating library or producing a library or data set of conditions that we can test based on a flow reactor system. And then we can start using an initial algorithm for optimization to come up with a set of conditions that will allow us to achieve that target, whether it's controlled pressure, temperature, feed ratio, and so on. And this will involve, obviously, initially a computational time that involves the initial design. But then in real time, we need to have a computational pathway to change that algorithm as we gather the data during the reaction. So whether the reaction is done in minutes, hours, or days, or simply done in sequences where we can get different types of products that can be analyzed by NMR, IR, Raman as fast as we can then generate that library so that the algorithm or can go towards data mining, machine learning, if it's a simple subset, to come up with a new set of conditions that we can iterate. So this can, in principle, be applied. It has been applied towards drug development by several um, operations or in literature. It's called QSAR or optimization space. This is just emerging. And here you can see the Intersect organization that we're creating at Oak Ridge. So what we want to achieve with the Intersect is have a automated autonomous self-driving facility that can be integrated between the different science domains. Ours is one domain, which is a continuous flow reactor. Other domains involve spectroscopic analysis, microscopy, or even automated synthesis of catalysts. And this is a big initiative of Oak Ridge National Lab in that we want to connect those autonomous self-driving experiments in a system that they're all talking to each other, or they are available to computational scientists and development of AI or algorithm purveyors based on uh, computational facilities, excellent computational facilities we have here at Oak Ridge. So that means we need to integrate this in a system that communicates in a common language. What we're looking at is development of nodes or edge analysis nodes that allow us to have the data talking between experiments. So in this hardware, which we actually have in our lab, we started with a system based on Snapdragon chemistry. We have several reactors that allow us to control the temperature, the flow rate, the volume, the path towards monitoring this based on different wireless monitoring systems that can be integrated in one server, the Lab OS, which was developed. Here we can have one reactant and another reactant pump in a reactor, monitor the dosing rate and the conditions of that reactor, temperature, flow rate, pressure, using the Lab iOS. We then connect different analytical tools, as I'll explain to you in this schematic diagram, towards producing signals or spectroscopic or even microscopic data that then provides feedback so that we can monitor what's happening to the reaction or what yields we're getting. Key to this also is the use of auto sampler or easy sampler systems, where we dose the amount of solvent that is introduced during the reaction, for example, or taking aliquots or samples as the products are produced. But nevertheless, as shown in the schematic diagram below, we are developing here a feedback mechanism to have a continuous loop on that continuous flow process, so we can optimize it in real time or collect fractions which we can analyze and investigate separately with different analytical techniques, and then plot the data and so on. This latter part that I'm mentioning to you is quite tedious and slow. And that is why the need for us to put tandem tabletop um, um, tabletop instruments next to the reactor. So you can see surrounding this reactor, we have been interfacing NMR, IR, Raman, surface plasma spectroscopy setup, ESR, fluorescence, and the list goes on. We have about 10 instruments we want to use as a monitoring system and collect data. Here, again, a scheme of that process in a bigger picture. So essentially what we want to achieve is to have a real-time in situ in operando analysis of the reaction and reaction products as they are produced. And we do this by gathering the spectroscopic signatures, whether we're focusing on one peak or the whole spectra itself, and then analyzing the product distribution, the yield, okay, the rate by which a product is produced or a byproduct is produced or need to be removed in real time. So in principle, if we can do this synchronous with the flow rate or how slow we can make the reaction, then we can produce a real-time data that in fact, we can plug in an algorithm if we want to. So all these things are in development, and we are partnering also with a number of companies that are interested in this regime. There are several flow reactors available other than the Snapdragon system. from Thales Nano to VaporTech series and Meteor to Lido, and several of the instruments that are portable and can be connected to a continuous flow sampler are in development. And so here is just a picture. It's actually a movie, but maybe we don't have enough time to show this movie. But we have created a lab here at Oak Ridge National Lab that allows us to use this hardware, take advantage of the computational facilities and the expertise in AI, machine learning, and deep learning at Oak Ridge to produce a high throughput conditions in the laboratory of the future. So with that, I'll be happy to answer any of your questions. And as I post on my front slide, you can also contact me by email. And here are some references. So thank you, and I'll be happy to answer your questions.
Thank you so very much, Rigoberto. What an excellent way to round out this symposium. I can see that we've had some questions through already, so I'll move straight into the Q&A session. Your first question, what procedures are unique in flow chemistry that are not found in batch scale synthesis?
Okay, very good. So obviously in flow, you need a pipe. A pipe means you have a flow rate, you have insulation, okay? And you can also control what you feed to it. Unlike a batch reaction where everything's put together either at one time or in sequence, everything is put together. And you need an impeller basically to mix them. So a flow rate becomes a chemical engineering operation, a unit operation where you can control the temperature, the pressure, and depending on how narrow that pipe is, or if you pack it with solid material, it becomes a packed bed or heterogeneous column. So those are the salient differences between the two.
Fantastic. And another question for you. How do you control multi-phase synthesis in flow reaction conditions?
Okay, so multi-phase synthesis, minimum of two, let's say a gas and a liquid, as I've shown you earlier, this can be done by having a column within a column where that inside column has a diffusion property, let's say a membrane, that allows you to control the diffusion, let's say, of gases in and out of the inner column. Another way, a multi-phase condition, of course, can be controlled is based on the can liquefy natural gas or cool certain fluids to supercritical fluid conditions. One can control the phase behavior or reaction in a continuous flow reaction.
Brilliant stuff. Just one more question for you then, just as I'm aware of the time. Can these methods be used for the synthesis of nanomaterials?
Absolutely. Nanomaterials, typically we look at them at the range of 100 nanometers or less. Also, as I've started my talk actually with comparing polymers as nanomaterials. Nanomaterials can be in the form of oxide particles, metal, gold, carbon nanoparticles, carbon nanotubes, um, um, nanocellulose, etc. So one thing one can do is, of course, to produce nanobubbles, which is not easy, and then use that nanobubbles as a separate phase or reactor. Or the use of micelles, as been shown earlier. Micelles are of the entity of hundreds of nanometers or less, but they can also be controlled in terms of their stability as nanoemulsions. Another way you can control reaction conditions to produce nanomaterials is based on gas phase synthesis, where you have a surface or surface support that contains catalysts, metal catalysts. Let's say when you're producing carbon-based materials based on a metal catalyst. Another way that nanomaterials, of course, can be controlled is based on the aspect ratio. So if you have a shear rate or a particular flow condition that elongates, one can achieve different types of anisotropic or even fibrous type of nanomaterials. And those things have yet to be demonstrated. In fact, as as a question. It is a challenge to all of you who would like to venture in using flow chemistry to make nanomaterials instead of the traditional batch reaction in a flask.
That is great. Thank you so very much. Unfortunately, that's all the time that we have for today. Any questions that we didn't have time to get to will be answered offline as soon as possible. And so that's it for Laboratory of the Future 2023. As mentioned throughout the day, all of the talks from today's event will be made available to view on demand for the next 30 days. You can access the talks via the same link that you used to access them today, and we'll be sure to pass on any further questions you submit through the system to the relevant speaker. That just leaves me to say thanks again, and we'll see you again at our next online symposium, Applications of Gene Editing 2023. Goodbye.